Hello, today we're going to be doing standard 5.1, which is on particles and their wave functions, and we're going to be doing problem 5.6 out of McIntyre. The problem states, for a particle in an infinite square well, calculate the probability of finding the particle in the range 3/4 L to L for each of the first three energy eigenstates. So the length of our square well is going to be L, and then we're going to be measuring the probability that it lands in the last quarter of this. So in order to find the desired probabilities that it requires, we need to first know what these energy eigenstates are. And here, since we know that the energy eigenstates are quantized, we have that phi n of x is equal to root 2 over L times sine of pi n x over L. And here we can now calculate the probability, and it just turns out that the probability of measuring particle from A to B is just the modulus squared. Integral from A to B of modulus squared of our energy eigenstate, the position representation, that is. So now that we have this, we can calculate each of the three probabilities using this formula. So first we have the probability of measuring it in the first energy eigenstate. Is the same integral set up now with using the first energy eigenstate, and we get modulus squared of it, which is 2 over L times sine squared of pi x over L. And when we evaluate our integral, we can either use parts or trig sub, but here I got this formula from the McIntyre integral table, and we pull the 2 over L out, and we evaluate the antiderivative from 3L over 4 to L, and we get 1/2, and that antiderivative is 1/2 x minus L over 2 pi times sine of pi x over L times cosine of pi x over L. And when we do the evaluation, we get that the probability is equal to 1/4 minus 1 over 2 pi, which is approximately 0.091, or about 1/10. So we can now do a similar process for the other two. The probability of measuring it in the second energy eigenstate is the same integral, now using the second energy eigenstate. And when we evaluate the integral using the same process, we get a probability of 1/4. And lastly, the probability of measuring the third energy eigenstate, doing the same process, gets us 1/4 plus 1 over 6 pi, which is approximately 0.303, so about 3/10. So lastly, let's try and analyze what these probabilities actually mean. And here this is a graphical representation taken from McIntyre that shows the probability densities for the first three energy eigenstates for a infinite square well of length L. And this is exactly what we're doing here. So now that we have these probability densities, we're actually just finding the area under the curve here. And now we can kind of compare to what we expect. So 3/4 L is approximately somewhere in here. And since this is just a bell shape, approximately a bell curve, with some changes thrown in, but now we know that this is definitely going to be less than 1/4, and it's actually going to be less than 1/8 because this is consistently decreasing. And we get 1/10 here, which is a little less than 1/8, a little less than 1/10, so it's approximately what we expect, so this value makes sense. And now getting a value of 1/4 for getting the secondary energy eigenstate makes complete sense why we get 1/4, because 3/4 L lands right here, which is exactly here at this antinode. So this is just half of this part of the curve, and since we have two copies, the area under the curve here is going to be 1/4. So this probability makes complete sense. And lastly, if we look at this one, 3/4 is going to land somewhere in here. So we know our value is going to be a little less than 1/3, but not by too much. And here we have about 1/300, so about 1/30th less. So 1/30th less than 1/3, which is exactly what we expect. We expect this little piece to be missing, so slightly less than 1/3 of the total area. So now that we've analyzed this, these probabilities make sense, and thank you.